everyone! Thank you so much for watching another episode of the Weaviate podcast. We have a super exciting one diving into some cutting-edge research on filtered vector search. Firstly, I'm super excited to be co-hosting this podcast with Abdel Rodriguez, a vector index researcher at Weaviate. Abdel, thank you so much for joining the podcast.
Thank you, Connor, for inviting me. Yes.
Awesome. And we are super excited to welcome Liana Patel, a Ph.D. student at Stanford University and lead author of ACORN, Performant and Predicate Agnostic Search over Vector Embeddings and Structured Data. Liana, thank you so much for joining the podcast.
Yeah, thank you. I know it's a bit of a long title.
Sorry, I got tripped up on data. That's not even a tough word, but awesome. So to kick things off, Liana, could you tell us about sort of how you got into Approximate Nearest Neighbor Search and what sparked your interest in it?
Yeah. So I remember kind of early in my PhD being broadly interested in systems for AI and ML. So I brainstormed really a whole bunch of ideas with my advisors. And as I started reading, this was one of the ideas, kind of one of the directions we thought about. And I kind of just started reading a bit more here. And I found that a lot of the indices are really fun to work with, or just kind of fun to read about, I guess. There's a lot of pretty cool systems work in the area and also a lot of interesting algorithmic and theory work. So I really liked that combination of things. And I really had a lot of fun just reading about some of the indices like HNSW, IVF, IVFPQ, LSH, etc. So kind of that's how it started. It was kind of just having fun, I guess, reading about some of these.
It's so exciting. And then maybe I'm curious also just like how your research journey began. Did you start maybe using like the FACE library or...
Yeah. So we implemented ACORN primarily in FACE. So yeah, that was the code base that we started with, and there's a lot of great other ones as well. But that was just the one that we picked.
Oh yeah, super cool. And I'm really curious to get your thoughts on things like Parlay ANN and all these kind of things as we dive into the details further in the podcast. But maybe as one more sort of introductory question, I'm very curious about filtered vector search, particularly something that maybe Abdel also wants to talk more about, some of the applications that we're seeing, but things like wanting to filter your vector search on price ranges or dates. What led you to this particular aspect of vector search?
Yeah, and I'd love to hear from your guys' perspective as well. I think like some of the early blog posts we read were from Weaviate and other vector databases. So it's really cool work. But I think it was an interesting problem. Like we had kind of read a bit about it. There were some prior works at the time when we were starting the project. And I was just kind of intrigued about it. It wasn't totally clear to me why pre and post filtering are not enough. When do these things fail? Like when can we just not use those? And it seems like a lot of systems were just using pre and post filtering as kind of the default baselines for hybrid search. It would seem like there's also like a number of workloads where these are really practical queries you might want to ask over your data. Like you have structured data, you have embeddings, and you want to do some joint search over them. And then we kind of started benchmarking, just kind of like running some simple experiments to try to understand performance here. And what we saw was these things can really really degrade performance from what you would expect from a typical ANN index like HNSW or IVF or LSH or another one. And so there is this pretty compelling problem, at least in our minds, of like, can we just kind of try to bridge this gap in performance? Like, can you get something that gives you hybrid search, but really the performance that you would expect from your ANN index? And it seemed like there were also workloads, kind of like that would benefit pretty clearly if we could do this. And so that's kind of where the interest started there.
Yeah, super cool. So I think this would transition perfectly into, starting to unpack the meat and potatoes of ACORN. And yeah, so could we maybe start at a high level of how ACORN extends HNSW and how it achieves this?
Yeah. So I guess maybe some background that would be helpful is like kind of the types of works that we were seeing in this space. So one was like pre and post filtering, which kind of I mentioned briefly. So there you're either using like some structured index or you're leveraging the vector index. So with pre-filtering, like first you do your filtering, then you do a brute force search over your vectors, which is the part that becomes inefficient when too many things pass your filter. And then with post-filtering, of course, first you're searching your vector index and then you do your filtering. So it's great that you can leverage the vector index, but then you have to do this type of search scope expansion to make sure that you actually can end up with the like K or the number of targets you want to retrieve after your filtering. And so they kind of have these trade-offs where if too many things pass the filter and pre-filtering, you get pretty degraded performance. You're doing a linear search over that remaining set. And then in post-filtering, you don't know how much you need to expand your search scope. And in some cases, it can be quite expensive. So that includes things like where you have low selectivity predicates. You might need to expand your search a lot. It also includes things like query correlation, which maybe we can come back to a little bit later. But basically, if your vector search, where like basically you do your vector search, that lands you in some space within the vector space. If that's far away from where your hybrid search target is, again, you need to do this like pretty expensive search scope expansion, which becomes expensive. So those were the kind of, I guess, what we'll call predicate agnostic baselines. And then there's also this other class of prior works, which are these specialized indices. And so they take this different approach to say, basically, like at construction, let's assume that we know that we have, some predicates, they're relatively a small set. And also, like, sometimes there's various types of constraints, like there will be equality-only predicates or specific operators that you have. And so if you have this knowledge during construction, then you can kind of do this type of brute force enumeration over your known predicates and try to modify your ANN index such that basically like you're ensuring that you can serve each one of your known predicates. And so, that can give you better performance than pre and post filtering in a bunch of cases. But you've introduced some of these assumptions that limit the type of query semantics you can have or the type of predicates essentially you can have. So for example, there's systems like filter disk ANN, you would have on the order of thousands of distinct predicates, which maybe sounds like a lot, but like for a bunch of use cases, for example, like price ranges, you want to filter, like some inventory and have your predicate be on the price. It's a continuous range, and like you don't really want to make that assumption. And so then, I guess this is kind of a very long detour, but basically the idea of ACORN is to, offer this performance. Like you want to kind of have like good performance, something that looks like an ANN index or just search over an ANN index, but also not make these assumptions during construction. And so that's the predicate agnostic piece. And essentially the way we do this is to kind of emulate what we call the Oracle partition index, which really is a simple idea. It's just basically we want to emulate search over an HNSW index or some ANN index. And the way to do this is basically we'll construct this index. For us, it looks like kind of an HNSW, but not quite, kind of like a denser HNSW almost with some important modifications. And the idea during search will then to traverse over this predicate subgraph, which is the subgraph over the index that's induced by the nodes that pass the query predicate. And so the idea is then to ensure during construction that these arbitrary predicate subgraphs emulate HNSW graphs. And so if we can do that well, then we're essentially emulating search over an HNSW, or the Oracle partition is what we call it. And we're doing this without actually ever building that or ever injecting this type of Oracle knowledge into the construction algorithm.
Yeah, I love the background you had, and maybe I can talk a little more about like our research when we were looking at different filtered ANN algorithms. Then Abdel can kind of jump in on the engineering, and then sort of we had like a funny discovery with our pre-filtering HNSW and what we had as we were digging into ACORN. But this, and I love how you touched on that background, and I maybe forgot to set up the question well. But previously we had filtered disk ANN where you needed to know the filters in advance, so you wanted to add extra connectivity to, and now ACORN has this predicate agnostic way to arbitrarily have any filter combination. You could have like OR filters, or the cardinality could just explode. And so maybe let me pass it to Abdel, if you could talk about kind of your first experiences with implementing ACORN, and maybe also touching on sort of, I think it was a funny discovery how we found that our pre-filtered HNSW was using this kind of candidate result thing instead of that linear scan. And if we could dive into all sorts of details like this.
Yeah, where should I start? So we were indeed exploring a bit, and actually Connor brought the topic about ACORN, and we find it's very interesting because, well, the predicate agnostic thing it's very powerful, right? So while doing it, we realized, no, but we realized the comparisons were a bit fuzzy for us because we were not actually doing pre or post filtering. We were using the full graph to guide the search and still only take into account those vectors that would pass the filter for our result sets. So yeah, then we had some totally different comparison in mind, and yeah, it's very interesting now for us to see how could we squeeze really all the details to make it like really performant. So one question from the engineering point of view is how do you see if you are only expanding your search through the vectors that would pass the filter, you mentioned you could have these regions in your vector sets where the hybrid search occurs, and some black regions where you don't have anything. How do you see your your the way you build your graph would connect those regions? How could you jump between those regions? This is something very interesting to me because
Yeah. This is a super great question, and something that I think is pretty cool about HNSW. Like basically, you have kind of these dense upper layers, dense in the sense that relative to like your parameter M, they're pretty highly connected. And also, they're like kind of these long range links just based on the random sampling process of how you sample nodes. So they give you these long range links across the graph. And so I think this helps a lot with what you're referring to as kind of like, having these spaces without things that you pass, what we would call query correlation. And so we like benchmarked this in the paper. And you can get with ACORN, like when you use this type of identification process and then also the pruning that we have, you can actually like robustly perform with like negative query correlation where you're far away, your vector search target is far away from the hybrid search target. But also like you can perform well with positive query correlation, or also like the random case, the random label case. Hopefully that gives you a little bit of intuition, but maybe
it's actually it brings some light in our research. Yes,
yeah.
Thank you.
Yeah, super. I think maybe also for our listeners, if we could maybe also just kind of dig a little further into kind of the Two-Hop, the neighbor of neighbors heuristic, and then maybe continue our zoom in of details of connecting regions and things. Liana, could you give us a little more detail about sort of this kind of idea of you either, ACORN, maybe also the question would be good to separate ACORN 1 and ACORN gamma and how the two variations of the algorithm use this heuristic?
Yeah. So you're talking specifically about like the neighbor pruning thing. So I'll try to explain that a little bit better. So I'll start with acorn gamma and then also touch on acorn one. So acorn gamma. So again, like the main goal of the construction is basically to ensure that these arbitrary predicate subgraphs, they look something like an HNSW. And a piece that's important to understand the intuition here is kind of just a high-level sketch of the search algorithm, which is basically like we're performing this filtering over the neighbor lists, which I think is what Abdel is also mentioning. And so because we're performing this filtering, the construction should intuitively like densify the graph. We want to have more neighbors in our neighbor list, so that then we perform this filtering and we still have like some reasonable number of candidate nodes left to traverse to, and that's important for the search convergence. So the construction algorithm, like the high-level sketch, is basically we're performing this densification. It's parameterized by this factor gamma. So in HNSW, you collect m, at most m neighbors per node. And acorn gamma, it'll be m times gamma. And then, that creates a challenge because now we've just blown up the neighbor lists. And now we have this problem of the space footprint of the index. And HNSW is also memory resident. So, like this actually matters. So kind of we need to do something to solve that. And so that's when the pruning comes in. So we're trying to essentially shrink the neighbor lists so that they're now smaller. The index space footprint is smaller as well. And the way we do that is, I guess like one natural question to ask, right, is like, can you just apply HNSW's pruning, which is this RNG based, this RNG pruning strategy. I can maybe go into some detail, maybe I can skip those details, but kind of there's details in the paper, and we find like you don't want to do this in general. Like you want to have some type of pruning strategy that's amenable to hybrid search. And the RNG-based approximation, it's great for like vector search in general, and it's been shown empirically. But for hybrid search, because you're doing this filtering during the greedy search algorithm, you don't necessarily want to do that. And so what we do instead is we have this heuristic, which will do this pruning by essentially trying to retain the closest neighbors to a node exactly, and then approximate the latter half of the neighbor list in a way where we can recover nodes but store fewer nodes in the index. And there's really two pieces of the pruning. So one is like the actual pruning we do. There's really two pieces of like the strategy. One is the actual pruning we do during the construction, and then the second piece is actually matching the search algorithm or making the search algorithm accommodate that by doing this search expansion. And so the construction algorithm is basically we iterate over the nodes from the m beta index to the end. So the first m beta will just be retained exactly in the index. And then the latter half, we do this type of pruning where if a neighbor is, this is all within some node's neighbor list. Let's say that node is V. So if a neighbor in this neighbor list is already a neighbor of V, then we would prune it. And then during the search algorithm, we also do this expansion where within this latter half of the sublist, or not half, but like from m beta to the end, we'll do this expansion where we'll look at neighbors of neighbors. And so that allows us to then recover these candidates while still retaining a smaller sublist in the index itself.
Yeah, it's so cool. This kind of changed the traversal with how you expand the neighbors of neighbors. And then also it really inspires me thinking about just like, I don't know if like graph analytics, like I don't know if you've ever had an interest in if seeing like certain nodes that just have like a high centrality score, or like that's almost what it motivates me to think about is looking at the neighborhoods in more of like a graph analytics perspective. Have you ever kind of put that hat on, so to say?
Yeah, that's interesting. I don't know that we've looked at it particularly in that way. I guess, yeah, could you explain more? What were you thinking there?
Hey, I don't know. I just like this whole, like the whole kind of like you're looking at like the neighbors of neighbors, and now you have like this two-hop expansion. Just the way
Yeah.
that you're thinking about the connectivity of the graph is really. I haven't really seen any works. Maybe Abdel could jump in if you've seen something like that, but mostly I think HNSW is just kind of like distance pruning, and there's not too much sort of like analysis of like how important is this node to the graph. Maybe it's with the engineering system, it's related to when you're deleting nodes and you have like the tombstone cleanup, and but that node was like a particularly important node for like hopping to other nodes in the graph. And maybe something else that Abdel does in our research team is he draws these pictures of nodes. Is one of Abdel's super skills is drawing out a like a vector
That shows
traversal.
up a
And
lot.
yeah. Yeah. So yeah, maybe my question is, Abdul, what was your first thought when you came across this kind of like hop, two hops type of way of thinking about proximity graph connectivity?
So I first my first thoughts about it was that this was a way to, let's say, reduce the memory footprint of your graph. So you have more connections now, and you don't want to store all of them in on each node.
Yeah.
So instead, you reuse the capacity of finding them in the second hop, and you don't put it on the first hop. So you don't want to end up with gigabytes lost just in connections, because it's a big graph already, and the information is there. You don't have to write it twice. That's the way I got it. I hope I'm not confused about it, Liana. You
Yeah,
can
no, that's
elaborate
exactly
more.
right. And kind of like the intuition, which has been studied, maybe this is kind of what Connor was touching on. For example, like with KNN graphs, and really like a lot of work within this space is just that neighbors and neighbors are likely to be neighbors of a node, and so that's kind of the key intuition that we're leveraging here, which allows us to do this and kind of like cut the exactly what Abdel said, like reduce the number of nodes we're actually storing, but then still recover them later on.
The good question would be, as Connor said, let's say you start then deleting nodes. I don't know if you did this kind of experiments. When you delete, then maybe you do lose information because it was supposed. So some nodes were supposed to be discoverable in the second hop, but you remove those complete branches. Then, yeah, I don't know if you did some experimentation with this or.
So here, you're right. So we're removing in the construction, but what compensates for this is the search algorithm, where we then do the expansion in the latter half.
Hmm.
So we do this expansion exactly where we do the compression within the sublist of the construction algorithm. And so that's kind of the key here, is that that allows us to then recover these nodes again.
I had one question on this, and like, have you thought about right now we have kind of like this two hop, and I was kind of curious if just you could go sort of k hop, like three hop, four hop, just to
Yeah.
when it's a really selective filter. Yeah.
Yeah, that's a good question. So, yeah, theoretically, like you could do arbitrarily many hops, but something to consider is like one, you should use pre-filtering. There are cases at
Hmm.
low selectivity where you should just pre-filter. Like it's the most efficient thing you can do, and it also gives you an exact search mechanism. So, kind of, if you start doing like 3 hops or 4 hops, you could do that, but you're probably better off just doing the pre-filtering method for very low selectivity. And so, what we would recommend for like ACORN is you set this gamma threshold. It could be something related to like 1 over the minimum selectivity you want to serve. And then below that, you pre-filter.
Hmm. And then this almost motivates me back. Well, so this almost kind of motivates. We earlier talked about kind of the you don't need to know about the filters a priori, and I think that's a big part of why Acorn is such a breakthrough, is because the past algorithms you definitely needed to know that, and but with the selectivity to route pre-filtering, maybe you also kind of need to at least have some meta information about the most commonly occurring filters, and
Yeah,
then
yeah. So that's right. So you don't need to know the predicates in terms of the operators or the cardinality, but it is useful in general to have some sense of the selectivity at which you would want to use. Um, you would want to use to expand your neighbor list to parameterize gamma, and then to also decide this cost model of when to use pre-filtering as opposed to acorn gamma or acorn one. Yeah.
yeah, it's so interesting. I guess I'm also really curious about. Well, I have this algorithm that I'm working on, and and so I've had the opportunity. I asked Magdalene about this, and I've been asking, super excited to ask you about this as well. Is kind of like you have a particular filter that you want to increase the connectivity on, and so you search with that filter with pre-filtering, and then you just add those edges. You add those nearest neighbors as additional edges, and so I'm curious if you could have like an acorn graph that you build, and then you sort of, after it's built, you then later on have this, you try to repair it and make strengthen the predicate subgraph. And I love that predicate subgraph. I think that's just the perfect way of thinking about this. And you can maybe do some like post analysis to strengthen the connectivity of that particular filter graph.
It's definitely possible, but kind of when you do that, you're now making the construction, I guess, predicate dependent, which
Mm,
maybe
yeah.
is okay if that's what you want to do. But you could actually, like, if you just have a small set of predicates you want to serve, you could also just actually build the Oracle partition index, which would just be like HNSW indices over each one of these sets. The downside of that is that, of course, if your sets are not mutually exclusive, you're going to have some redundancy there. You could, I mean, if the main use case here is for like low selectivity predicates, though, it's probably best to just pre-filter. But kind of that's something that could be measured empirically. Yeah.
I love what you're saying about the Oracle partition index, and I think that's like the dream is like put the Oracle partition index somehow into the whole graph, and yeah, and I think this two hop this hop membership kind of way to think about it is really brilliant. And yeah, so maybe before coming into experiments, Abdul, do you have any more questions about kind of the workings of Acorn? Maybe kind of like like Acorn one traversal, anything like this? Yeah.
So I was also wondering a bit about, so normally you don't care too much about, well, you don't care too much now, but you are not really too careful about the selection of the uh, neighborhood size you select when you build HNSW, because it's okay a little bit more connections will maybe make your search a little bit slower, but that's okay. But in this case, we have some kind of so we have neighbors of neighbors. So if you use 32, suddenly you have 32 times 32 neighbors. If you use 64, then it's it's a combinatorial problem. So did you have some insights about how to select this to not affect performance so bad about, and I guess the selectivity of the filters will play a role here, but I
Yeah.
just wonder if you have some theory about it. Yeah.
Yeah, so this is definitely very important. So what you're touching on here is that HNSW has a bounded degree, that's M. Of course, like you can shift that slightly and it shouldn't really affect performance too much. And what's important here is that ACORN also ensures this bounded degree at search time. So where during construction, we don't do this, right? So we have M times gamma, but you'll always have at most M. So the degree is bounded during search, and that's a difference from the way HNSW handles it. But that's why this like combinatorial problem of kind of as you increase M, the idea that you could be potentially now searching over M times gamma things per node during search, that never actually happens because there's a truncation step of the neighbor list during search. And so that's one important piece. And then the other thing you touched on was kind of like, what's the right way to set these parameters? You know, like is ACORN very sensitive to them? What we find is that in general, so there's M beta and gamma. Gamma kind of, there's a couple of recommendations we have for that. So like one would be choosing the minimum selectivity you want to target for ACORN gamma before you pre-filter. M beta, we find that the search performance is relatively not so sensitive. And empirically on the benchmark data sets we test on, some good heuristics are like small multiples of M. So something like M or 2M, if M is like maybe 64 or 32 on SIF 1 million and paper that we tested on, those are pretty reasonable choices.
Yeah, super quiet. Yeah, I found a pretty good result with just using like gamma for, I think it's for 10 for the one over the estimate. I'm just like remembering the paper now. So there was one other part of the paper I really want to ask you more about that I thought was really novel, is the time complexity, the runtime complexity analysis that you did. It was really, I think it's such a nice how you described the algorithm before the experiments. You really get into the math of that. Maybe, I don't know if we'd be able to describe all that math in the podcast, but maybe at a high level, like what have you learned from doing that? Just
Yeah. This is a fun piece. Maybe I can just try to give a little bit of intuition. It'd be nice to have a whiteboard if you wanted to go into the deeper math pieces, but I won't go there. So the intuition with the search complexity is the search algorithm itself is like kind of simple. And like the base case is just performing filtering over your neighbor list and then doing a greedy search, which looks very similar to HNSW search. And then there's this small change in the this expansion step that you have on the levels that were compressed. But the simple case where you're just doing filtering, right? Essentially what happens is you have this predicate subgraph that you're trying to traverse to, but you're starting from this predefined entry point at the top of the ACORN graph. And so there's really two stages of the search traversal. The first is to just perform filtering basically on the top levels. And so every time I'm on a level and the node I'm at doesn't have any neighbors that pass my predicate, I'm just going to end up like stopping my search on that level and dropping down to the next one. So it's really just a filter on these top levels. And so that gives you like this constant of like the log 1 over s, which I won't go into. And then the second piece is like once you've actually reached the predicate subgraph. So now you've found a node that passes your predicate, and you're going to start doing this filtered greedy search every time traversing to a node that again passes your predicate. And so this is the piece where I'm traversing over the predicate subgraph. And there, the search complexity, it looks very similar to HNSW search complexity, except that for every distance computation that I perform, I also have to do a little bit of filtering along with it. And in general, the distance computation is kind of what we would assume to be the expensive piece. So the filtering should be pretty reasonable to handle.
I hope this doesn't distract too much, but I just had something click for me in that analysis back to what we were talking about earlier. But I think with me, I have a bit of a hard time just understanding HNSW to begin with. And then the
Yeah.
hierarchical part of it is like, I just totally forget about that part.
Yeah.
How important is, and I think this is also related to the query, the correlation stuff that we'll get into in a bit, but maybe for our listeners, that's referring to if the filter is correlated with the vector space as well, just to set up, probably it's important for this talk, but can you tell us more about like the role of the hierarchy of HNSW in ACORN search?
Yeah. So maybe I can talk about kind of just like the hierarchicalness in HNSW in general. And it's really pretty cool. So, HNSW stands for Hierarchical Navigable Small Worlds. So the smallest piece of that is just a small world, which is where, like you have a pretty low degree of separation between any two nodes. So there's these short paths that are connecting any two nodes within the graph. And that's great, but then there's this navigability piece. So not all small worlds are navigable, meaning that just because this short path exists, I can't say for sure that my greedy search heuristic is going to find this short path. And so the navigability piece of this is the navigable small worlds will have this property where actually, like, I can find these short paths using some decentralized search heuristic, like a greedy search. Um, and so kind of there's like a lot of work in this area, which I think is really cool, but maybe to just summarize some of the pieces. There was a lot of work on navigable small worlds, but they gave you this like polylog search complexity. And so HNSW introduced this hierarchical structure, which really does a couple of things. One was it helped with the actual greedy search path in the sense that rather than just starting from some arbitrary point in this path, you start from this top level, and the top level intuitively represents these nodes that have high degree. They have high degree because they're repeated across multiple levels, and they have m edges on each of the levels. And so they're kind of like these, hubs in the graph where you can get from one hub to like many, many different nodes. And so they give you this higher degree of connectivity, or like basically you can make these long range jumps across the graph. And so that actually helps with the greedy search convergence, which is pretty cool. And then the other piece that was pretty cool was that now you have these bounded degrees across levels. And so that also helps with the search efficiency. And so these are reasons why the hierarchicalness is important for HNSW. And essentially, like the same hierarchical structure is what we use in ACORN. So actually, we're sampling at the same exact level probabilities as HNSW. And so those pieces look very similar. Yeah.
And that was another detail in the paper I'd love to talk more about. Is so you don't do any pruning on the higher layers, like layers one up. Is that correct? Yeah.
Right, that's right. So we targeted level 0. So level 0, it has all nodes in the graph, whereas as you go up the HNSW or the ACORN graph, you have fewer nodes per level, and that's something that is basically an exponential decay. So you have far fewer nodes at the top levels, and the bottommost level is the heaviest. And so that was the target for compression that we focused on. You could also apply compression on more levels, but it's just that there'll be smaller marginal gains from doing that. But it definitely can be done. Yeah.
Sorry, I just want to be sure I understood correctly. So what you're saying is that you are not doing compression on the higher levels, but you are still using the filter search on the higher levels. Okay.
Yes.
Good. That's also very good. Yeah.
Oh yeah, and my question is very similar to that as well. I'm curious about so you just turn off pruning, and then I also see with ACORN 1 that it says without HNSW pruning. Is that the same thing? Just like zero pruning?
Yeah, exactly. So the upper levels are just the expansion applied during construction to every neighbor list. And the pruning is only applied on those levels that are compressed, which probably for level 0, you generally want to do that to not blow up the space footprint. And then ACORN 1, so the way to view it is, ACORN gamma is this construction heavy algorithm where we've done this neighbor list expansion, and that costs like basically a gamma log gamma factor during construction. Essentially, it does increase the time to index. And that's great because once we do that, we can do this pretty simple filtering based search strategy that is quite quick. And so that's why I'm saying ACORN Gamma is construction heavy, but relatively search light. And ACORN 1 reverses that. So it's construction light. Essentially, you don't do pruning. You don't do the HNSW pruning. You don't do any type of pruning. And so you're just storing those M nodes that you have. And so the TTI is heavily reduced and even below what you would have for HNSW. And then to compensate for that, now you do a search expansion during search. And so what we see is that ACORN 1 essentially approximates the search performance of ACORN Gamma, but is much better for resource constraint settings where maybe you really care about decreasing your time to index.
My first thing is I love the time to index. This paper was the first place I had seen it, and I brought that to our chat, and then everyone was using it, and I was like, nice. But yeah, so that's super interesting, and yeah, I guess I'm just maybe want to zoom in just a little further on kind of how you turn off pruning with ACORN 1, and just because you still do change the construction a bit that way, correct? Or
right. So there's no pruning in ACORN 1. That's right.
So then do you have so then I guess I'm really curious what happens to the graphs when you do that. Like maybe you have certain nodes that end up with a really high number of edges, and I know you did all this analysis on like the average edges per node at each layer and things like this.
Yeah. No, so yeah, it's a good question, but you don't end up with anything that's ever going to be higher than M. The reason is because before you apply pruning, you still apply you still use the same strategy to collect candidate neighbors, and that will always be at most M. And for ACORN Gamma, that will be at most M times Gamma. And so for those candidate neighbor lists, respectively, like in ACORN Gamma and ACORN 1, then you apply pruning, in which case ACORN 1, there would just be no pruning, so you're left with that most M. So yeah, it's actually not an issue for that.
Oh, super. Just one more on this line of questioning. I'll pass it back to you, Abdel. I was curious about those. Well, firstly, if I have a correct understanding of this, that you also kind of add backwards edges. So, when I'm inserting Connor into the graph, I've connected with not myself, but you connect with M neighbors, and then I insert Abdel and Liana into the graph, and you two might connect me as your neighbor. So then I would also then add the M+1, yeah.
That's right. Yeah. So this is the standard insertion algorithm from HNSW, actually, where you find the candidate neighbors, you do some pruning. Then once you choose the neighbors you're actually going to add, the actual insertion algorithm will add the edges bidirectionally. So both from Connor to Abdel and Abdel to Connor.
Yeah, super. Abdel, do you have any more questions on that before we maybe come into experiments?
Not exactly on this. But I don't know if we are talking next about experimental analysis and so on. So I also have some questions there, but not about this. Yes.
Yeah, super cool. I even maybe want to set this up by saying that this, I think we should start with the correlation, the query filter correlation thing. It's like a connection of filtered vector search with maybe out of distribution, because it has this distribution perspective on it. And I just want to sort of pay the hat tip to it before we even dive in. Liana, could you tell us about the experimental analysis of ACORN?
Yeah. So did you want me to start on the correlation piece, or maybe just generally first?
Oh, I suppose however you think the story goes. I sort of read it like it.
Yeah, no, I like talking about correlation too, so that sounds good. But yeah, I guess to maybe summarize kind of what we saw in the experimental analysis. So we tested in really two ways. One was against a lot of prior works, which includes specialized indices that I had mentioned. And that setting was particularly on these data sets that have low cardinality predicate sets. And so we tested in that setting against things like NHQ, and then also others like Filter Discana, and they have two algorithms, and several other baselines. And we see there that ACORN outperforms these specialized indices by something like 2 to 3x higher queries per second, higher throughput at a given fixed recall. And what was also cool in that setting was that we're actually able to simulate this oracle partition method. So because these predicate sets were relatively small, we could actually just build an HNSW over each one of the known predicate sets and try to measure this empirically to compare how we do compared to this oracle, which is theoretically ideal, but not actually practical for many settings. And we see that ACORN gamma actually can approximate that pretty well, and is the closest amongst the methods that we saw to approximate the Oracle partition. So that was the first setting. And then the second setting was really these more complex data sets where the specialized indices they can't perform in these settings because the predicate sets are high cardinality, and there's also various types of operators such as things like regex matches, ors, equals, many other things. And so those settings, the baselines here were pre and post filtering, and we found pretty substantial performance gains using ACORN. So that was something like 20 to 1000x. And there's a lot of micro benchmarks that we looked at in terms of how ACORN performs under variations in selectivity and things like the dataset's size or scale, and also query correlation. And I think query correlation is one cool piece of this. And so maybe I'll just try to explain briefly, or try to paint the picture more clearly, like what we're actually looking at there with query correlation. And so the idea here is that one simple setting you can imagine here when you have search over both embeddings and structured data is that the things that pass your filter, your predicate, they're uniformly distributed across your vector space. And so if you're in that setting, post filtering, kind of what you would expect to do is maybe just oversample, or basically just expand your search scope by a factor of the selectivity, right? So to be maybe concrete, let's say I have a bunch of t-shirts in my embedding space. They're all embedded images. And I have some attribute like the color of every t-shirt. So it's either going to be blue or it's going to be red. And let's assume these are all uniformly distributed across my space. So if I was to post filter here and I have a query, some query image, and my label is blue, instead of collecting k things, I'll just collect k times 2, let's say. And then I'll apply my filter after that, and I'll probably get about k things that pass my predicate, and that should be good. So that's a simple case of basically no correlation. It's where these things are uniformly distributed. The labels are uniformly distributed across the space. The more interesting case is where you actually have some form of clustering. And so what that looks like is where the things that pass my predicate, they cluster within my vector space relative to the vectors themselves. So you can imagine here that my query vector, it can be either close to this predicate cluster, i.e. the cluster of things that pass my predicate, or it can be far away. And if it's close, then what that means is that I do my vector search, that lands me pretty much in the space of things I want to be for hybrid search 2, and I'm in pretty good shape. But if the query vector is far away from that target cluster, then I would have to do this very lengthy search scope expansion to actually reach that target of the vector space that I want to be in to find my hybrid search targets. And so that's the case of negative query correlation. And we test in these 3 settings. It seems like maybe Abdel has a question, but
No, but finish, please finish.
So yeah, we test in these 3 settings, and what was cool was that ACORN can perform in the negative query correlation case, the no correlation, and also positive query correlation case, and it offers substantial gains in all 3 of those.
So if I may ask, I'm trying to wrap my mind around it. So let's say, as you said, you have this correlation of your query of your filters, and you land with an entry point through the hierarchy on a region where you don't have any nodes, right? That passes the filter. Then how would your 2 hops expansion take you to the region you need? So I can imagine that in some cases, if you have a really selective filter and you end up away from your region, you won't find anything at all because you don't have a path. Is this something that, yeah?
Yeah, I mean, this is a really good question. And I think this is the piece that's very cool here. It's because we have this hierarchical graph, like H and SW, where, the intuition that Abdel is mentioning is I'm really far away from the thing that I want to get to. Like, how am I going to get there? Like, even if I do a 2-hop search expansion, I may be more than 2 hops away. But with H and SW and ACORN, you have these long range lengths at the top of your graph. So this gives you like kind of these hops that take you very far away from where you are. And so you can actually like hop to this predicate cluster in a way, and some of the settings that we've seen, right?
So put
So
simple,
go ahead.
so put simple, if you would have regular HNSW with pulse filtering, let's say, and you know for sure that you are close to these regions because of the hierarchical, how is ACORN of any advantage? Because you could say, okay, I know I'm going to land in this region.
Yeah.
I could pulse filter a little bit because I'm in the region, so most of the vectors will pass the filter. So if I do a regular HNSW, I should have enough information there. So I'm trying to understand how is ACORN helping in this case.
So you're talking about here this case where you have like high positive query correlation. Am I understanding that right?
Yes.
Right. So there's a more marginal gain between ACORN and the post filtering method, right? So that's where we can expect that post filtering will perform well. But oftentimes you can't assume that. And I would say like this isn't just kind of an adversarial case. It's also like common workloads that you might see. Like for example, one is maybe like outlier detection or trying to find maybe mislabeled examples. So let's say you have images of cats and dogs. You can imagine like these things can be embedded, and maybe you have two clusters, one of like cats or cat vectors that look like cats, right? And then one of your dog images, and those are both in vector space. And maybe the question I want to ask is like, find me the images that look like basically ones that were mislabeled. They should be cats, but they were labeled dogs or something like that. So I'll have this image that looks like a cat, but I want to find the label that was a dog. And so that's a case where you can't assume necessarily that you have high positive query correlation. And really, the system should be able to handle all cases robustly and just be able to handle that under the hood.
Interesting. Yes. Thank you.
That last one, yeah, that whole it almost reminds me of like embeddings and classifiers, that kind of thinking of the outlier detection, and it's very interesting how that out of distribution detection, how you're unifying that with filtered vector search. That's really something I hadn't thought of before. I was sort of always testing uniformly distributed and hadn't considered another case, but yes, I think that's a super. And I guess kind of one thing I wanted to comment on is sort of the like the analysis of the graphs that you do. It really makes me think about sort of the tooling around observing HNSW. Like we've always had things like the average degree of nodes, and then how much memory is the graph using, and then you just have queries per second, just like unfiltered. But you describe things like benchmarking, as we discussed earlier, how many neighbors you have on levels 0, 1, 2, and 3. And now I think what we'll see with the future of like Datadog for vector databases is like more of this like fine grained like per filter query search. And I'm curious, maybe like as you're studying this stuff, like the kind of things you want to see about the graph, and if you have any thoughts on how this might change the tooling that you'd like to like observe a HNSW index.
Yeah, that's a great question. I think like as I was working on some of these experiments and debugging, I was just kind of, printing these very, very long logs of everything I could possibly want to know. But some of the things that were pretty helpful, definitely the neighbor list size, like total, but then also sometimes the filtered lists that you have. And then in general, like it was pretty helpful to get some semblance of what the predicate subgraphs look like. So this matters, especially if you have a couple, like maybe some common predicates that you're going to be repeatedly serving, and you want to kind of make sure that these work well. So that's something that you can actually look at and like actually just get these predicate subgraphs, like print them out, look at properties of them, things like connectivity, the neighbor list size, etc. And I would say like kind of all the things that you might look at HNSW, they could also apply here. Of course, like one of the you know the benchmarks matter a lot, and kind of just like being able to measure these empirically. But yeah, ideally, like you can also build these graphs and kind of not do this detailed analysis for every single one of your predicates, but maybe the common ones that that you're using repeatedly.
Yeah, I love that kind of thing. I think that's so powerful, having that kind of analysis and view into it. Awesome. So I think that's both of our questions on experiments, and so an anchoring topic that I really am excited to ask you about, and I sort of have two levels to this, with the headline being compound AI systems. So I love this phrasing. I think I agree heavily with the team behind it around this thinking about multi-layer LLM programs that interact with retrieval databases, tools, and maybe moving away from the agents abstraction into compound AI systems, or how it encapsulates all this kind of stuff. And maybe like the transition question I wanted to ask firstly is, like if your work in compound AI systems, if that connects with the filtered vector search, like how you see that connection, if you're going to continue to pursue that. And, yeah.
Yeah, definitely. I think the search and retrieval components are really interesting here. And I think, broadly, one of the threads that this work touched on and kind of I'm also generally interested in is, how do we use both structured and unstructured data and kind of augment whatever types of AI systems or LM systems that we're building with these like very vast corpuses of knowledge that may take the form of many different modalities. So I think that's a pretty cool thing that there's really a lot to explore there.
Yeah, I think that's so interesting as well. It almost, yeah, like different sources of data. Thinking about how I think right now most of the kind of RAG systems, they're very rare to see filtered vector search being a part of the system or separating data into multiple collections. It's usually just like one big chunk of information, and so that's something that I'm really looking forward to, is seeing RAG systems that use filter information as well. And so sort of the other question I want to ask is pretty broad, and just like, what kind of things are you up to now with compound AI systems? Like, what directions for the future excite you the most? Yeah.
Yeah. So maybe I kind of like hinted at one, which is kind of looking at queries, or kind of like what these types of query systems with LLMs might look like when we have these many types of data or many modalities of data that could take the form of tabular data, but also maybe embedding data, also even just various types of unstructured data like freeform text or other modalities that we see now. And I think the general theme here is that these are just all individual components of this larger system, where we're not just treating the models as these monolithic components that basically have all the knowledge that we could possibly need, but rather there's these pretty complex interactions between all these different pieces. And in many cases, it's also just non-trivial how to make the best use of various forms of data, like the tabular data or some forms of unstructured data. So I think there's really a pretty large design space here to explore.
Uh, yeah, it's so inspiring. I'm curious, like, do you think about these hybrid systems that maybe like route queries? So it's like you're routing it to a vector database, or you route it to like a SQL type of query, and is that sort of the yeah?
Yeah, I think we're seeing really a bit of both. I think they're both pretty interesting. Yeah, I guess I don't have super opinionated thoughts there yet.
Oh, yeah, I've had a ton of fun exploring this kind of thing too, and yeah, like just I think the query routing, or how you might combine information from two different types of data source search, I think is definitely one of the biggest topics emerging, and something that really inspires me a ton as well.
Yeah.
Um, awesome. So yeah, it's so exciting to be seeing this compound AI systems thing. I really like just seeing all the research that's coming out, and yeah, I guess I don't really have too many questions there. Just other than just I'm so excited to see how it develops. We love DSPy and all these
Yeah,
kind of like agent
a lot
things.
of very cool work. Yeah.
Yeah, awesome. Well, Liana, Abdel, thank you so much for joining the Weaviate podcast. This is such a fun discussion into ACORN and all the exciting things that are happening in filtered vector search. Thank you so much.
Yeah, thank
Thanks
you.
to you too. Yeah.